Здравствуйте.
Здравствуйте. So I suppose we can start. Hello everyone, my name is Alina Boyko and I am your moderator for today's session. Today we have three sessions, and the first session is mathematical modeling and image processing. So your chairs for today, Alexander Krivoshein, Professor Alexander Krivoshein. And your presentation should be not more than 12 minutes and 3 minutes for questions. All audience during the presentation be muted, and after the end of the presentation, you can unmute yourself and ask your question. Also, you can write your question in chat in Zoom and also in comments in YouTube. So I suppose we can start. Maybe Alexander wants to tell something.
Hello, everyone. I just correct you that we have two chairs. It is me and Yelena Kotina. So I think we can start.
Maybe I announce of Alexander. I think the first presentation is parameterization of orthogonal, hexagonal, asymmetric low-pass filters, and presenter is Alexander Krivoshein. Please, Alexander.
Yes, thank you. So first, I'd like to thank the organizers for the opportunity to present my talk, even in this situation. So let's start. I will speak about low-pass filters with some special properties. And first of all, I'd like to say where it is useful. And it is useful in the construction of wavelets. What is wavelets? We start with one single function. We consider all its duadic derivations and integer translations. And if our function is good enough, then this wavelet system can form a good representation system. I mean, for instance, it can be an orthogonal wavelet basis. So any function in O2 can be represented using usual orthogonal decomposition. This is one-dimensional case. What's changed in multi-dimensional case? Not much. We just need to dilate our function with some special dilation matrix. This is an integer valued matrix whose eigenvalues are greater than 1 in modulus. For instance, we just can take a matrix that is equal to 2 times identity matrix. If we start with good initial function, then we can get an orthogonal wavelet basis. So wavelets have become a standard tool in signal analysis techniques. There are some benefits. Some of them are listed here, like fast algorithms, like sparse signal representation. It means that almost all coefficients for smooth signal are almost 0, and we have good potential for compression. Also, it is good time frequency localization properties compared to standard Fourier analysis. And growing amount of applications, for instance, the most recent are like extracting features using wavelet transform for neural networks and so on. So growing amount of application requires some new wavelets with special properties. And how to construct such wavelets? Well, the story starts with a refinable function. So it is a starting point. It is a utility function, and it satisfies so-called refinement equation. It means that function is can be represented as a linear combination of its own dilated and shifted copies. And good properties of wavelets are mostly inherited from this function phi. Moreover, these properties can good properties of phi depend on this finite sequence of coefficients ak. And this sequence or the corresponding trigonometric polynomial is called a low-pass filter. So the point is, if we start with good low-pass filter, then we potentially can construct a good wavelet system. So what kind of properties I'd like to provide for wavelets or for low-pass filter? First of all, it is symmetry. In a few words, this means that symmetric function is just rotated, is just invariant with respect to rotation or reflections. And it is very desirable property in applications. There are some benefits of this property, like symmetric wavelets produce less visual artifacts compared to non-symmetric wavelets in image processing. Also, there are some computational efficiency of symmetric wavelets. They have more computational efficiency compared to just usual wavelets, and so on. The usual stuff, how to deal with symmetry, is a symmetry group. And in our case, it is a group of unimodular matrices, integer valued, which forms a group under a matrix multiplication. And also there are one technical properties like how this group is connected with matrix dilation. Well, in some sense, it should be matrices from the group should be interchangeable with matrix in a sense of this relation. So function is symmetric with respect to the origin if this relation is valid, which means that function is invariant with respect to some rotations or reflections. And simple cases are like point symmetry, which means that function is just even, axis symmetry, which means that function is just even with respect to each coordinate. But I will consider some special case. It is two-dimensional case and threefold hexagonal symmetry group. Hexagonally symmetric function is just invariant with respect to rotation by 2 pi over 3. Why hexagonal symmetry? Well, hexagonal image processing, when we deal with hexagonal lattices and not usual square lattices, they have some advantages over the usual image processing. And there are some papers, there are some books about these advantages. For instance, like hexagonal image processing, practical approach monograph. Next, why we consider only some special cases, I will consider only one dilation matrix in this talk and only one symmetry group. Well, this is because orthogonality plus symmetry are very restrictive properties together. So there are no general methods for such constructions. I mean, for construction of such low-pass filters with orthogonality plus symmetry. But for small coefficient supports, which are most desirable in applications, filters with orthogonality and symmetry can be fully characterized, or they can get we can obtain parameterization, and that's what I will do in this talk. Well, let's go deep into details. I fix the dilation matrices. It is 2 times identity. Then we should fix a special set of vectors formally they are representatives of this quotient group, Z2 over MZ2, quotient group or factor group. So they are just fixed. To providing orthogonality for wavelets, it is necessary to provide this type of relation. So this is some kind of quadratic involved equation. Next, for symmetry for refinable function will be provided if we provide the analogous relation for the low pass filter. So coefficients should be connected in some sense, in the sense of this relation. And also one technical property like sum rule of order n. This property is heavily connected with the order of approximation of wavelet system. And sum rule, at least of order 1, should always be valid for orthogonal refinable function, for orthogonality. This means just low pass filter or its trigonometric polynomial should have some specific values at some specific points. Well, if we get parameterization, then we can find some parameters which allows us to maximize some quantities like approximation order or smoothness or something else. I will maximize smoothness in terms of Sobolev sense, which means that it is a maximal new maximal exponent which can be set here such that this integral is finite. So this is just Fourier transform of a function. It is somehow connected with the usual smoothness, but in terms of this smoothness, it is more easy to compute this value. Let's start with toy example. Well, let's start with a filter whose coefficient support is inside the set -1, 1 squared. Well, when we deal with two-dimensional case, it is convenient to draw a filter as a matrix. So it is coefficients, it is indices of coefficients. And let us consider a concrete example. This is filter which has 4 non-zero coefficients, and 3 of them are equal to each other, like BBB. This filter is automatically hexagonally symmetric. And so we just no need to worry about it because we take this kind of template for this filter. Next, we just write down equations for orthogonality, equations for sum rule, and try to solve it. In this case, it is easy. So only one choice of parameters when a, b equal to 1 over 4 give us a solution. But when we consider some not so easy examples, the solution is much more involved. So for instance, if we consider support like -2, 2 squared, then hexagonal symmetric template is like this. There are 6 equations which comes from sum rule and orthogonality conditions. And here, full parameterization of solution is possible. It can be write down. So it is a set of relations. We start from 2 parameters, alpha, beta, and we just can write down the solution of these 6 equations. And smoothness can be maximized in this case for some specific set of parameters. Also, I consider the next support. It is like snowflake support. It was considered in the literature. Again, the same steps can be done. I will not write down the solution, but the known smoothness, the best known smoothness for this type of support was like 0.89. But with parameterization,
2 minutes.
Yes, thank you. With parameterization, we can find the better solution with better smoothness for a refinable function. Okay, this is this solution. This is a graph of the refinable function. So it is clear that it's invariant with respect to rotation by 2 pi over 3. The graph is plotted on hexagonal lattice, where the hexagonal symmetry is more natural to see. Well, a few words about how to construct wavelets. The general theme is known, but the key problem is the following. So we just need to extend one row of trigonometric polynomials. So we have filter, and we can equivalently write it down as a row of some trigonometric polynomials. Well, the key problem is to extend this row up to the whole matrices of trigonometric polynomials such that it is unitary in this sense. If we succeed, then wavelets are just easy to obtain from these trigonometric polynomials. What is the problem? The problem is that if we try to extend these matrices up to a square matrix, then even the possibility of such extension is an open problem. So of course, there are no general algorithms how to extend this matrix. And there are some choices what to do. For instance, one special choice when this matrix has some special form, like the first row is such that one element is just a number, for instance, just number 1. And the second option is to relax orthogonality condition. Well, of course, we don't get an orthogonal wavelets, but we can get so-called tight wavelet frames. What does it mean? They are not orthogonal, but orthogonal-like decomposition is valid. So any function can be represented as this type of decomposition, which is coincide with orthogonal decomposition, but the functions are not orthogonal, and the decomposition is not unique. But it is widely used in application, so it is also a good choice concerning the construction of such wavelets. So here are the main points, and yes, thank you for your attention.
Thank you.
Yes, very much for very interesting presentation, Alexander. And a small question. What about any applications for some image processing? Maybe can you show us some example of applying such sort of methods?
Well, unfortunately, I'm not so experienced in application. I just do some theory, but I have some application examples. But yes, it is a good point to think about it, especially when I talk about hexagonal symmetric wavelets and hexagonal image processing. Maybe there are some interesting things compared to usual image processing, but it is for future work. So at the moment,
I think that it's very interesting and very interesting work. Thank you for your presentation again.
Thank you.
Thank you, Alexander. And so our next presentation is Alexey, yes? Oh, no.
Yes.
Yes.
Hello, colleague. I present my presentation, remote sensing data processing for plant production control. Currently, the use of remote sensing data is becoming more perspective and actual for the effective solution of problems in information support of crop production, precision agriculture, and ecology. Both satellite images and aerial photographs can serve as carriers of such information. Methods of processing and analysis of remote sensing allow rapid detection of emergency in agriculture fields, assess the state of crops and reclamation systems, manage crops yields, and contribute to solving other environment problems. The main remote sensing advantage is the ability to quickly collect data with high information content of their values. Remote sensing is particularly suitable for monitoring large areas used in agriculture. Sustainability of agriculture production largely depends on the management of soil heterogeneity and field topography. Precision agriculture provides automation of such management using information technology. In 2000 Hatfield identified three main classes of variation that exist of the agriculture field. Natural soil and topography, random, example, weather, controlled application of agrochemical. Taken into account all three components, agro-technological decisions are taken together. There are many open sources with process satellite images, so it's advisable to consider remote sensing data obtained and processing to control the plant production process using the example of aerial photography. A set of tasks related to the management of agro ecosystems and requiring the receipt and preliminary processing of remote sensing data is considered of the basis of experimental agriculture fields located of the territory of the branch of the Agrophysical Research Institute in the Minkovo, Gachinsky Rayon. Among such tasks, the suffices to single out of the main ones: monitoring the crop status, differential application of fertilizers and agrochemicals, yield forecast, calculation of vegetation indices, monitoring of meliorative system, non-working plant detection for drainage system, determination of overgrowing dimensions of water stagnation of a drainage system chain, soil erosion detection, planning of repair work, and other. It is necessary to obtain georeferences orthophoto maps in the visible and near infrared range for information support of the listed problems. In addition, aerophotos must be with high resolution because same tasks have scientific research nature. There is also a need for a digital terrain model for some same task. In recent years, Russia has rapidly developed the production of unmanned aerial vehicle. The market is present with great variety for research work. Since 2015, we using the GeoScan 401 helicopter type, which allows for automatic flights and shooting as well in as high quality images. And that is greatly simplified the task solved. In addition to the copter, this system includes the onboard complex, payload, and ground control station. The general chain for remote sensing data obtained and processing on Agrophysical Research Institute experimental fields can be represented by four main steps. Steps 1, collecting of the request from our colleagues to aerial photographs planning. And T-stage experimental fields for aerial photography are determined. The optimal shooting date is selected. In addition, a knowledge base for each declared fields is formatted. Field number, crop characteristics, experimental description available with the aerial photographs for this field. Flight timeable is begin compiled. On step 2, implementation of flights on schedule. At this stage, the flight team departs to the experimental fields for aerial photography on appointment dates. At the same time, important stage section are the equipment prepared, the flight plan development, the flight implementation and support using a ground control station, as well as the storage of obtained images. On step 3, pre-processing aerial photographs, this stage they implement automatically using special software that comes bundled with a managed aerial system. And step 4, downloading the received and processed data as well as a knowledge base into a single interactive information system where all available experimental research information will be displayed for future scientific work. The advantage of such system are not only in the exchanging data between our departments, but also its economic potential. It sends for the other institute and organization in the future to store their data or to use the download experimental data. Let's look at the task we solve in more details. Monitoring the state of crops allows you to quickly identify problem area of crop development at the early stages of development and develop a strategy for field processing. The use of high precision orthophotos has shown its significant effectivity in solving a number of plants production control problems in compared with the traditional agriculture method. For example, we can build a map of distribution plants nitrogen content, as well as to generate a technology map that allows for differential fertilization. It should be noted that the Agrophysical Research Institute studies have shown a significant economic efficiency of the differential in comparison with traditional fertilization. Monitoring the state of crops during the growing season allows you to predict the possible yield of cultivated crops. The calculation of vegetation indices allows us to look beyond the visible range and predict the development of disease, find area of wheat vegetation and deal with them in a different way. Monitoring of reclaimed land using UAV makes it easy to identify problem area in the field. Find the point of blockage of underground drainage with high accuracy. The resulting high precision digital elevation models allow us to find area of stagnation of water on the field and simulate the movement of water flows on the surface. Digital terrain model also allow you to find area of soil erosion and accurately measuring the parameters. Accurate calculation of the volume of overground and siltation of channel allow us to make reasonable estimates for the repair of reclamation systems without leaving the area. The use of remote sensing seems quite an effective approach to solving the wide range of problems in the interest of agriculture related to monitoring the state of agro landscapes, assessing and managing their productivity. At the same time, aerial photography helps to increase the mobility of data acquisition, reduce financial cost and labor cost, speed up the conduct and increase the level of experimental research while ensuring high reliability and completeness of the data. Thank you for your attention. You can send your question to our emails.
Thank you. It's very interesting. Maybe somebody have questions?
Yes, I have one question. What mathematical processing method are you going to apply in your further work?
For calculating differential technology map for fertilizer, we use mathematical processing. We compare nitrogen content in crops and using value of nitrogen, we calculate a technology map. And we use our mathematical models to determination of water stagnation.
Thank you. Thank you.
Any question?
If nobody have questions, I suppose we can continue. Thank you, Alexey.
Thank you.
And our next presentation is Albina Akhmedyanova.
Mathematical modeling of cyclic chemical compounds. Yeah. Yes.
Just a second, Albina, we can hear you.
Now it's okay?
Yes, yes.
I am presenting to your attention my work, Mathematical Modeling of Cyclochemical Compounds. The determination in the experiment of the thermodynamic quantities of organic compounds is often difficult and sometimes impossible. In addition, among this amount of huge experimental information, there are also unreliable data. In addition, this huge amount of experimental information, there are also unreliable data. The task of creating universal high-precision theoretical methods for calculation and prediction the properties of chemical compounds. The purpose and objectives of this study is development of mathematical apparatus for calculation the enthalpy of formation based on the use of homodesmic reactions. Objectives: development of an algorithm for constructing a basis of GDR for different classes of organic compounds based on the analysis of the molecular graph of a chemical compound. Creation of software to determine the basis of the GDR to increase the reliability of the theoretical definition of the standard enthalpy of chemical compound formation. The design of the basis of homodesmic reactions consists of the following steps. Converting information from the database. This information consists of the adjacency matrix and the group composition of the connection. Counting the number of units of Z in the adjacency matrix and determine their allocation in the matrix. Obtaining various variants of adjacency matrix by sequentially zeroing the units in the matrix, zeroing units based on the algorithm of allocation of Z units of me. Extension the adjacency matrix due to attachment and end groups. Selection of suitable end groups from the database and obtaining the right parts of homodesmic reactions. Initialization the right parts of the received reaction from the database. The enthalpy calculation for formation of all obtained compounds. Algorithm for construction a basis for gomodesmic reactions for acyclic compounds. Firstly, presented all possible variants of unfolded molecule, which is obtained from the initial break one of the cycle linkage. Identify all possible combinations of internal groups forming a chemical compounds. Second, for each term, choose the end groups from those groups are presented in the initial null chemical compounds, or construct a new one by the addition of valence bound atoms from the right part of the GDR. Third, to determine the regions of the initial chemical compound, take into account the group composition of the products of the right part of the GDR. Regions are made up of the end groups, including all the products. Third, to put the stoichiometric coefficients on the GDR according to the group balance, preserving the number of group internal and end of each type. Next, we consider the schematic finding all possible combination of internal groups by the example of cyclobutane molecule. As you can see on the screen, it contains two internal groups, B28 and B25, and also we need end groups K1, K4, and K8 to our work. To break the cycle in a molecule, one break is enough, as you can see from the slide number 7. The first variant is the breaking of one bond between B28 groups in the cyclic cyclobutane compound. Our software are presented on this slide in the molecule cyclobutane. In this slide, you can see the relations between table in the database, and also our database and program was registered in this year. Conclusions. An algorithm for construction a GDR basis for different classes of organic compounds based on an analysis of the molecular graph of the chemical compounds has been developed, and software for determining the GDR basis was created to increase the reliability of the theoretical determination of the standard enthalpy of chemical compound formation. Thank you for your attention.
Thank you, and thank you for translation actually in Russian. So maybe any questions?
Yes, just a simple question. What is enthalpy?
Enthalpy of formation is a chemical thermodynamic in chemistry, we can calculate enthalpy of formation some compounds. For example, in this slide, you can see the enthalpy of formation of cyclobutane HF0.
This is some kind of energy or what?
Yes, it's energy. It's a characteristic of chemical compounds.
Well, but in a physics sense, what does it mean? How much energy can be expanded or into the space, or what?
It's function of thermodynamic system. Enthalpy. It's sum from internal energy and another energy.
Okay.
Energy of chemical compounds. When we broke the cycle, our enthalpy change. I can answer you more at my email if you can.
In a few words, I understand. Yeah, some kind of inner energy. Yeah. Okay.
I think it's very interesting, but very special topic for us. Yes.
Yes. Thank you.
Thank you for your presentation.
Thank you, everyone. I suppose we can finish our short sections. So thank you. Now we have a break for 15 minutes, for 20 minutes actually. And or you can discuss anything what you want, but in English, please. You can stay here and watch our next two sections.
Okay, thank you.
Алина, здравствуйте.
Здравствуйте.
Алина, я вас попрошу вести первое заседание, да, следующей секции, а я буду вести следующее. Так что вы объявляли мой доклад, а я ваш доклад.
Хорошо.
Спасибо.
Здравствуйте, Евгений Игоревич.
Здравствуйте всем.
Hello, everyone. I'm sorry, I have the second translation. So maybe we can start, or maybe first presenter try to share your screen.
Yes, okay. Just a moment.
Ruslan, are you hear me?
Yes, can you hear me? Hello?
Hello, hello.
Yeah, okay. Can you see it?
Yes, yes.
Ruslan, excuse me.
Yes.
Ladies and gentlemen, first of all, let us start the first session of
I'm sorry you freeze. Евгений Игоревич, вы меня слышите? Okay. I suppose we should wait. And can you please write your real name here? Because we can see you and we don't understand who are you.
Oh, I will stop the demonstration so we can see Evgeny Igorevich when he will reconnect.
Thank you. Maybe I tell some few words about the rules. So for your presentation, you have not more than 12 minutes and 3 minutes for questions. And our presentation should be in English, questions too. And also when you ask questions, please turn on your camera and write your real name because we want to see you and know who are you.
Is it okay that I actually don't have the camera on this computer?
Okay.
I'm sorry.
If you don't have, okay.
I can make another connection from the phone, but I don't think it's necessary.
Okay, don't do this. You are first one. Don't do this.
Okay.
I suppose we should wait 1 minute more.
Maybe I call Evgeny Igorevich and ask what,
If you can, okay.
what is, okay, just a moment. Well, the phone is unreachable.
Yeah.
Well, that's very strange.
Okay, I hope he's okay. So
Okay, okay, maybe 1 more minute and just
maybe
start probably.
yeah, also you can, I don't tell this, you can write your questions in chat in Zoom, and you, for our YouTube audience, hello, we can see you, but you can see us. So you can write your questions in comments. Please do this because we want some questions. So for this part of sections, informatics and control processes, I am your chair. And for second one is Veremey Evgeny, Professor Veremey Evgeny. And I think we should start. Yeah. And our first presentation is Sebastianov Ruslan, and he will talk about multiple pose visual position of the undereckated mobile robot. Ruslan,
Yes.
yeah, you can start sharing your screen.
Okay, again, can you see it?
Yes, yes.
Well, good morning once again, dear colleagues. I will tell you a little bit about our method of visual positioning of the mobile robot. Well, of course, all of you know that visual sensors become more and more popular. It can be cameras mounted on robots or external static cameras. And another noticeable thing about modern control system is more and more strict and complex requirements and restrictions to the quality of control and to the control dynamics. So here we present some combination of the classic visual feedback method and our so-called multipurpose regulators that can meet a set of requirements to the motion dynamics. Let us consider a classic two-wheel robot, or it may be a tank chassis. The important thing here is that it is controlled by two guided wheels by setting their velocity, or in the dynamics by setting their voltage if it is the electric motors. We consider simplified linear dynamics model with constant disturbance, and the only nonlinearity here is the rotation matrix R in the kinematics part. And we assume that the robot has a camera rigidly mounted on the body. The task is to put the robot in front of some external visual marker, like one of these Aruka markers, starting from some arbitrary initial position. Important thing here is that we use visual information from the camera directly in the feedback loop. That is, the actual task is to achieve the desired position of the marker projections in the camera image, like on this plot with square markers. So we want the marker projection from here. This is the initial position to become this one in our image. And that will mean that the robot is in front of the marker. The classic approach, this problem is so-called visual serrating method. We can write the equation describing the dynamics of the image points based on the velocity of the robot. The goal is to achieve the desired positions of these points. So let us introduce the projection errors. And the classic visual serrating approach is to take V vector as this proportional to the L matrix to the inverse multiplied by E. And therefore, we achieve the exponential stabilities, the convergence of the errors to 0. But this approach assumes that we have ideal actuator that can provide the desired velocity instantly, and it doesn't make into account the dynamics of the plant. So how we can take it into account? Let us introduce our so-called multipurpose regulator for our task. First three equations of the regulator are asymptotic observers. For the velocity, for the position of the robot, and for the projection errors. Their role is not only the state estimations, but by modifying the tunable parameters of the observers, we can control the reaction to the external disturbances. Equations 4 and 5 represent the so-called dynamic character. It defines overall strategy of the reaction to the disturbance. It can play a role of the filter when it reduces the control reactions, for example, to the periodic disturbance, or it can be the actual character that minimizes the effect of the disturbance. In this work, we will use it to neglect the constant step disturbance. Finally, the last equation is control signal, providing overall stability of the system. One of the main advantages of such multi-purpose structure is that we can independently solve tasks of tuning the parameters affecting different aspects of the control quality. So the task becomes more simpler. In order to provide the stability of the system, here are some restrictions of the regulator tunable parameters. Using Lyapunov's method, it can be shown that KE matrix must be equal to the transposed L. Other parameters must be positive definite matrices to achieve stability. And the further search is based on the particular requirements to the dynamics. Now, a few words about the dynamic character. Again, here we want to provide this aesthetic property, in particular to fight constant step disturbance like side wind. So if you look at the character in the transfer function form and do some derivations, we can show that the character matrices must satisfy these conditions to, to fight the step disturbance. And of course, important thing that alpha matrix must be Hurwitz. Now, let me show some small results of the computer modeling to this regulator. We consider the simplest dynamics of the robot with unit matrices. Yes, it may look kind of synthetic example, but this is just for the illustration. And here are some numeric values of the regulator parameters, but I don't actually think that someone is interested in them. Let's just better look in the pictures. So figure 1 shows our initial setup. The initial marker positions on the image is this one, and we want it to become this one. So we want to go to make the robot in front of the marker. And with those parameters, without the disturbances, without the character, the actual trajectory of the points on the image plane is this one. So we really go in front of the marker quite smoothly, and we achieve the desired goal. Now let's make some complications. Let's add some constant disturbance, like these ones, to the dynamics. And we can see if we're not using the character, so we don't have the aesthetism, the robot fails to, to achieve the task. It can some noticeable error, so it's not actually in front of the marker. It goes a little bit sideways. But then when we turn the dynamic character, now it succeeds and it can go in front of the marker and everything is okay. It is the victory, hooray. So concluding my speech, here we have presented the special combination of the visual servering approach and multipurpose approach, particularly in the task of making robot move towards the visual marker. And as the computer modeling shows, our approach is actually working, at least in some conditions. So I guess thank you for your attention, and please ask questions.
Thank you. So actually, I have a short question. Did you try this model for real robots, or just a model and that's all?
For now, it's just a model, and we have some calculation in the Simulink, but of course, the applying it to the real robots is our probably main goal for now. So yes, to check, we have some real robots already, and we are going to test it, of course.
Okay, thank you. It's very interesting, actually.
Thank you.
Maybe any more questions? No? Evgeny Igorevich, are you come back? No. Okay, I have another question.
Okay.
So, did you try some other parameters? Can you please back for model, for first model? Yeah.
To regulator or the model of the robot?
Okay. Did you try change some another values and other parameters and try to do this model, or what you do?
Yeah, of course, we tried, but I'm sorry that I have no pictures. It is actually very interesting to, to get the idea how change of parameters affect the dynamics. Of course, it affects, but sorry, I don't have pictures. Well, I can say that if you, the main idea is that when you make the observer matrices bigger, in values, they start to fight the dynamics more and more. So when you make it really big, you can, and you don't notice the disturbance at all. But of course, it must be some, I don't know, values that can be really implemented. You cannot implement the arbitrary big parameters, but yes, they affect the dynamics, of course.
Okay, thank you. It's very interesting topic. So thank you for your presentation. If nobody have questions, no?
Oh, Evgeny Igorevich, hello.
I had some problems with my computer.
Sorry,
that's all right.
Okay, we already, I tell everything I wanted to tell. So I think, thank you for your attention, and I will stop the demonstration.
Yeah, thank you. Evgeny Igorevich won't tell something for us. Yeah, you can tell now.
No. I have no problem now.
No. Okay. So we can continue, and our next presentation is Maria or Mikhail Smirnov. No, they're not here. It's very bad. So I suppose we should wait them because we have timing. Maybe somebody can.
Алина, я сейчас спрошу у Маши, я позвоню Маше, спрошу, что там у них случилось.
Спасибо.
Алина, там препятствие непреодолимое, поэтому у них не получается с докладом.
Они вообще не будут выступать, да, получается?
Не будут выступать.
Окей, хорошо. So we can wait 15 minutes.
Yes.
12 minutes. Maybe somebody won't tell us something. No?
I can.
Who told us? I can see you.
One moment, please. Yaroslav.
Hello.
Yaroslav, are you ready to make your presentation now?
Yes.
No. We can't change our we can change our presentation. You just can tell us something, discuss something, because we have time and we can change your presentation. Мы не можем поменять время презентации, у нас есть жесткий тайминг, поэтому мы просто можем обсудить что-либо, пока мы ждем времени, можем просто что-то обсудить.
Yes, Alina, I understand.
Жди своей очереди, короче. Расписание есть расписание.
It's for our YouTube audience. Yeah. Maybe we can check our next presentation. It's Evgeny Igorevich, are you here? Okay. And Irina Pototskaya, yeah, are you hear me? No?
Yes, I can hear you.
Great. And Alexander, yeah? Are you hear me too?
Yeah, I hear.
Okay, thank you. Nobody want to talk about something. Maybe we can talk in Russian because we have a break.
Maybe. But what about?
Don't know. Если вы видели, то в перерывах у нас стихи, это стихи Зубова, настоящие стихи Зубова. В предыдущих днях, может быть, вы слышали песни Зубова, песни на стихи Зубова.
Мы не слышали, но мы знаем, что Зубов писал стихи в большом количестве.
Мы тут иногда включаем.
Да, мы в курсе.
Интересно.
Да.
На самом деле, сегодня на YouTube нас смотрит больше всего человек.
Алина, я попробую пока включить
Давайте.
презентацию, посмотрю, пойдет у меня, то может опять засыпаться. Так, видно?
Запускается. Да, видно.
Ага, все, пока выключу. Okay, Alina, could I start my talking?
Yes, yes.
Okay.
Oh, I introduce you.
Yeah.
So, Professor Evgeny Veremey with presentation Marine Vehicles Automatic Control based on Optimal Damping Concept. So, you can start.
Okay, could you see my screen now?
Yes.
Okay. Ladies and gentlemen, nice to greet you. It gives me a great pleasure to present to your attention our joint report with Professor Margarita Sotnikova with the title Marine Vehicles Automatic Control based on Optimal Damping Concept. This is contents of my report, introduction, control problems for marine vessels I would like to present to your attention, and some base position of optimal damping concept, Zubov's optimal damping concept, and practical OD based track and control problem, and I'm going to make some conclusions. So, all practical problems connected with marine transportation systems are well known. And it is necessary to know that optimization approach is one of the most commonly used analytical and numerical tools in the recent years to design control systems of various types. In our opinion, such a situation can be explained by universality, flexibility, and convenience of modern optimization methods with respect to relevant practical implementations of control theory. Among the various optimization methods, the optimal damping concept proposed by Vladimir Ivanovich Zubov deserves particular attention. The main position of this theory were proposed by Zubov in the early 60s. Here you can see three initial Zubov's works where the optimal damping concept was presented firstly. We believe that this ideology was ahead of its time and was undeservedly underutilized for practical control problem solving. Yeah, and this work is one of the attempts to overcome this omission. So let us consider a mathematical model, universal mathematical model, which can be applied for the marine vessel's motion presentation. This is robot-like systems where V is velocities, eta, this is includes position parameters, displacements, and angles of the vehicle in the fixed frame. Tau, this is control actions, D, external disturbances, and all matrices of inertia, damping, Coriolis centripetal temps, gravitational and buoyancy forces, and matrix of rotation are given. Well, let us consider the main practical problems which can be solved with respect to the motion of the marine vehicles. First of all, this is stabilization of the zero equilibrium position with no disturbances. We need to design the feedback controller which provides global asymptotic stability of this position. The second problem is tracking control, where we have desirable vessel's motion, and we need to construct feedback control to provide also zero equilibrium, but with respect to the tracking error for our motion. A third problem, this is dynamic positioning. This is particular case with respect to tracking control where the desirable motion is equal to fixed point in Rn space. And at last, the path following problem, where we have given curve in Rn, which is parameterized by the real parameter mu. And also we are going to provide global asymptotic stability of zero equilibrium position with respect to the distance from the real motion to the given K. Okay, all these problems can be solved using optimization approach, and optimization approach can be presented in two forms. First of all, this is classical form where we have integral given integral functional to be minimized on the motion of the closed loop system using nonlinear feedback control law. First of all, we have provide asymptotic stability, and this is convenient to make using Bellman concept, and all know the main difficulties connected with the Bellman concept application. We need to solve a very complicated AJB equation, which is the system of partial differential equations, and to realize this solution in real time is impossible, practically impossible. Other concept, this is optimal concept proposed by Vladimir Ivanovich Zubov. Here we have no initial integral functional, but we have functional to be damped proposed by Zubov, which consists of two parts. Here the function V, this is Lyapunov function really, actually, and this part is given by the positive definite function f0, which have zero values only if x and u are zero. If this construction is given, satisfying some additional conditions, then we can find optimal damping controller in the following form, and let notice that this controller can be realized in real time. This is essentially more simpler than to solve equation connected with Bellman concept. To implement Zubov's damping theory, we propose firstly to consider track and control problem, which is connected with a given motion of the marine vessels defined by the following equation. Introducing the error, tracking error, we can to rewrite the equations of the marine vessels in the form 1. And using optimal damping concept, it is possible to propose the OD, optimal damping controller, in the following form. And if the dimension of U is small, we can use the solution of this problem on the finite net. This can be done or analytically or numerically, never essential problems. For example, if the optimal point is the inner point of the admissible set U, so the solution of this problem can be transformed to the solution of nonlinear equation with respect to the current control U. We have a lot of examples for this approach application, both for tracking control problem and stabilization problem. Unfortunately, I have no time and no place to propose to your attention the results of the practical problems solution of these examples. Nevertheless, a lot of examples are used, a lot of modeling results we have, and we propose our result to practical engineers in Concept Aurora here for our Chinese colleagues, and we are sure that our results will be implemented in practice. So I can make the following conclusions. The aim of this work is to discuss some questions connected with various utilization of modern optimization ideology for modeling analysis and synthesis, and correspondent mathematically formalized problems are widely implemented in practice and are considered in numerous scientific publications. Among the various optimization approach, optimal damping concept deserves particular attention. This concept was proposed by Zubov, and in our opinion, now this ideology is very convenient and can be implemented in a wide region of practical solutions or practical problems connected with the motion of marine vehicles. In our paper, some efforts are made to apply the optimal damping approach for various marine controllers design procedures, and central attention is paid to the example of such application for the solution of the tracking control problem. Both direct numerical and analytical decisions are discussed. Okay, thank you for your attention. I am ready to,
thank you. Nice picture.
Try to answer to your questions.
Nice picture, actually. So somebody have questions? No questions? Actually, I'm too have no questions because it's very, very good presentation and we understand everything.
Excuse me.
Okay, okay.
A little question. You said that if the dimension of control is rather small, so you can apply some nets, yes. But if the dimension of control is rather big, will it be effective to apply your algorithm?
Yes, I believe that for marine control systems, for marine vehicles, the dimensions of U is not large than 3. For surface vehicles, we have only 1. This is vertical radar of the system. And for underwater vehicles, we can have bow radars, stern radars, not more than 3. And the final net is quite enough in using.
Thank you.
Any questions? No? Okay, thank you.
Thank you very much, dear colleague.
I suppose we can start next presentation. Start sharing. Just a second. Hello. You can start sharing. Yeah.
Hello. Nice to hear you and see. I can start?
Yes, yes. And I introduce you, and our next presentation is Professor Irina Potocka and multiplication algorithm for multivariate trigonometric series.
Okay. Do you see my presentation?
Yes, yes.
Yes, okay. So, good day, dear colleagues. I'm glad to present you our work titled Multiplication Algorithm for Multivariate Trigonometric Series. let us start with the relevance of the considering problem. Trigonometric series using in solving applied problems in many areas of knowledge is very effective. This approach is widely utilized in such fields as electrical engineering, in the theory of digital signal and image processing, and in other engineering problems. When constructing analytical theories of planetary motion, it is usually also necessary to decompose function into multivariate trigonometric series and calculate the series at some points. In all these cases, it is necessary to add and multiply the series and to collect similar terms. This action performance requires significant machine resources, processor time, and memory. In this regard, the development of analytical tools to reduce the consumption of these resources is very demanded. In this paper, we propose explicit formulas that allows us to computerize such evaluations and significantly reduce both the execution time and the required RAM. So, next slide. The suggested solution to the problem can be formulated as follows. Derivation of explicit formulas for the coefficients of the multivariate series product, which using with significantly reduced memory consumption and evaluation time. Second one is the implementation. The implementation of these formulas in software for solving applied problems can improve the software quality and competitiveness. This paper describes an algorithm for deriving such formulas. The resulting formulas are presented in a convenient form for software implementation. It's a statement of the problem, mathematical set of the problem. Let us consider two multivariate series, one with different numbers argument of K and P, for which the equalities 2 are satisfied. In addition, we assume that both series are reduced, and definition of reduced series you can see below. The series is said to be reduced if its coefficients with the first non-zero index are zeros if this index is negative. It follows inequalities for I and J that you can see in the slide. The main part of this work, of our work, is the algorithm for deriving explicit formulas. It includes sequential transformation, systematization, and generalization of the obtained formulas. This algorithm is described in details in the article. But now I want to focus on the result of this transformation. That is, we will write out the resulting explicit formulas and give the sequencing of the programming implementation. Sequencing, I mean sequencing, of course. So the resulting formulas one, let us present the obtained result. This result are given in the next 4 slides. For two multivariate series F and G given by formula 1, their product can be represented by formula 3. You can see the notations used here below on this slide. You can see notations here that we used. As the second slide resultant formula, it's the coefficients of the series product 3. You can see the coefficients alpha and beta in formula 4, and notations delta, it's formula 5. Next slide, it's a result in formula 2. And here we can see notations from previous slides, from previous formulas, and limits of sums, and other notations, and other notations. Okay, so and last resulting formulas slide. It's about the components of vector index L, and we can see here a lot of different kind of formulas, but it's very important formulas for very important formulas for resulting formulas. And now we okay, let's go to next slide. And now, for the convenience of software developers, we present our result as a step sequencing for the software implementation of Formula 3. I apologize, but for the convenience of perception, I will have to repeat resulting formulas one more. So, in accordance with the resulting formulas, to evaluate the series product 3, we should perform the following steps. First one, step 1, I can see. First of all, we need to evaluate the vector index L using formulas 9, 10, 11, and here K, P, and index vector I and G, it's known values. A second step, it's evaluation the values big AB and small AB using the formulas 9, 10, and 11 with stars. It's formulas to evaluate coefficients in coefficients alpha and beta. It's a second step. After that, for these coefficients, to evaluate these coefficients, we taken into account a vector L from first step, and the expression 12 and 13. It's a known values. A, B, you can see AG, BG, and small AB. It's a known values from series F and G. So at step 3, it's evaluation of the limits R and R big and R small for the sum 6. And we evaluate these values with using formulas 7. And here, A and G, it's a known values. Step 4, the values alpha and beta that are coefficients of a series product, we can evaluate on this step using the result of the previous steps and formulas 4 and 5. And the last step of the programming procedure, it's step 5. And here, the value of series product evaluation we can evaluate with using this formula 3. And in this formula, we know alpha, beta, L, and phi is a known vector. So, in conclusion, now we can sum up. The presented results allow us to computerize the evaluation process, and now to find the coefficients of the multivariate series product, not necessary to multiply this series by each other each time and collect similar terms. We desired, the desired result can be obtained immediately using the easy-to-program formula 3. Thus, the presence of explicit formulas allows us to greatly speed up the corresponding software products and reduce the amount of RAM. So, These advantages significantly increase the efficiency of the software and as a result, its competitiveness. We can, okay. At this point, my report is finished. Thank you for your attention, and I will be happy to answer your question if you have some questions. We have a lot of, I have very long list with describing our algorithm, but I think it's not necessary in the presentation. You can read it in article.
Thank you. Thank you. Thank you.
Thank you.
So, any questions? No questions.
I would like some. I would like to ask some question. First of all, could you estimate the computational benefit of proposed approach with respect to other approaches, with respect to well-known methods? I mean, no practical, but computational example.
It's about preference benefits of this method. Yes.
Yes.
Yes. It is a well-known fact that analytical formulas are better than any numericals one, and for multiple multiplication, the use of analytical formulas is definitely preferable because it's, but it's well-known fact because any numerical method, it's just some, how to say, I lost what, приближение.
Approximation.
Approximation, yes, thank you. So it's just approximation, but we have here analytical formulas, and you know, it's in all time, in all cases, it's much better than numerical.
Okay, thank you. And do you have some practical implementation for any mechanical, electrodynamical examples?
Yes, in planetary theories, motion. In planetary, yes. And
okay.
very good result. Will
thank you very much.
Will be good, yes. Thank you.
Thank you.
Thank you for your presentation.
Thank you.
So our next speaker is Fominih Alexander, and presentation is application of quasi-differential calculus to solving optimal control problems with non-smooth functional.
Thank you very much for the opportunity to make a presentation. My report is devoted to solving some optimal control problems, but not classical optimal control problems, but when the objective functional is non-smooth. So let us consider the statement of the problem. We have the ordinary differential equations 1 and the initial point 2. Here we have some assumptions. The first one is the finite terminal time t, and x is an n-dimensional continuous vector function of phase coordinates, and we assume that it has piecewise continuous and bounded on interval OT derivatives. And u from t is, as usual, control, and we also suppose that it is piecewise continuous and bounded on our interval. Besides, we suppose that vector functions f and their partial derivatives in control and in phase coordinates are continuous and in xu. And besides, we suppose that f is piecewise continuous in the variable t. The next assumption is the classical growth assumption on the right-hand side of the system, and it guarantees us that we will have the uniform in controls boundedness of the solutions. But instead of rather restrictive assumption 5, we can just assume that 5 dash is fulfilled. Having made these assumptions, let us recall the definition of a quasi-differentiable function. The quasi-differentiable function is such function, the increment of which is represented in this form. So here we have the meaning of the function at the initial point, and we have the maximum of the scalar product of the derivation and the vector sigma 1, which belongs to some set here. And we also have the analogous minimum of the scalar product. Here we say that these sets are convex and compact, and their pair is called the quasi-differential of the initial function. I have to say that the class of quasi-differentiable functions is very rich. For example, the finite number of superposition of maximum and minimum of continuously differentiable functions are quasi-differentiable. So these functions can be non-smooth. And let us also introduce the set of admissible controls. We will just consider the m-dimensional parallelepiped as admissible controls, but more complicated restrictions on controls can be also considered. We also denote x from TU the solution of the Cauchy problem for some the admissible control. And now we formulate the problem. So our aim is to find such a control U star, which belongs to the set of admissible controls and minimizes the terminal functional phi. And we assume that this functional phi is not continuously differentiable, but it can be non-smooth and it must be quasi-differentiable. We also will denote x star, the corresponding optimal trajectory of the system. Our method is firstly to apply the control parameterization and then to apply quasi-differentiable calculus. I will not describe the control parameterization in details. I will only say that we discretize the interval OT into equal parts or not equal parts, and instead of finding the function, we now aim to find the finite dimensional vector sigma. Instead of finding the function of control, we are aimed to find just the parameters, the constant parameters on the each of interval of discretization. Our system is now rewritten as follows, as is written in Formula 5, and here we'll only have the control parameter sigma. P is the rank of discretization, and we of course have the same initial condition. Now we see that our functional phi is now the functional only of this parameter sigma, and we must minimize it with respect to this parameter. Of course, it will be also quasi-differentiable in this parameter sigma. We, besides, additionally here assume that the function psi from x, it is rewritten here, is Lipschitz continuous on any bounded subsets of Re. And now we can have the natural question whether the solution of the discretized problem converges to the initial solution. We have here two well-known theorems. The first one is that the optimal value of the discretized problem converges to the optimal value of the initial problem. And the second one, if we have that the controls converge to some control U dashed, then U dashed is the optimal control of the initial problem, and we have the uniform converges in phase trajectories. So on practice, we must just solve the problem for different values of P and increase it to have the convergence. And the main theorem of my report is that functional phi from sigma is quasi-differentiable, and its quasi-differential is calculated by these formulas. I will not also describe them in details, but only say that with the help of differential equations which are represented here and these formulas, we can effectively calculate the quasi-differential of phi at each known point sigma. We will use this theorem in application our method. So I also will note that we can also take into account the restrictions in controls. It is made with the help of this auxiliary functional, and it is made with the penalty function. And it is important to know that in this problem, due to such the restrictions of controls, this functional will be the exact penalty function. It means that on practice, you don't have to increase lambda to infinity to have the convergence, but you can only take some positive constant parameter lambda 0 and work with it. So now we can formulate the necessary minimum condition of our problem. It is theorem 4 for the control sigma p star from the set of admissible controls to minimize our functional. It is necessary to have such an inclusion. I recall that these sets were introduced earlier in the concept of quasi-differential. Here are these sets. So if we have such an inclusion, we can guarantee that we have obtained a stationary point of the problems, and for some problems, for some class of problems, we can also guarantee that this stationary problem will be a global minimum. So now we formulate the quasi-differential descent method. Let the point on the kth iteration sigma kth be already constructed. If this minimum condition 7 is fulfilled, then the process is terminated. And otherwise, we construct the next point by this formula. Here we see that this is point on the previous iteration. Gamma k is the solution of one-dimensional minimization problem, and g from sigma is the direction of the quasi-differential descent of the functional phi at the point sigma k. So I want to note that all the steps here are constructive, and they are effective algorithm to solve all the auxiliary problems of this main algorithm. For example, one of the most important problem is to find the quasi-differential descent g. And it is done with the help of the quasi-differential calculus, which was introduced by Vladimir Fedorovich Demyanov. And for example, we can use Malazemov-Demyanov-Mitchell algorithm to solve this problem. Besides, we have some numerical examples. The examples here are simple just for demonstration, but I also have some more complicated examples, and the effectiveness of algorithm there was also proved. So the first example is linear. Here we have the initial condition, and here we have substantially non-smooth functional phi. So here we see that it is the superposition of maximum of two functions, this big function and 1, and this function is also substantially non-smooth. We have a lot of models here and minus models and so on. So the classical methods of continuously differentiable minimization is not applied here. Now we have, in this simple problem, we have obvious solution. It is, for example, the zero control. And we use the discretization of rank 0. So that means that instead of control, we just find the number. Sigma, it is sufficient for this problem. And let we have the initial control, then the initial value of the functional, and at the third iteration, we obtained the point U star, which is rather close to the true solution of this problem. And the corresponding value of the functional is also rather close to this value. And we have another a little bit more complicated example. It is nonlinear system, the initial condition, and here we also have the bounds on control. And it is required to minimize this functional. It is also non-smooth. And here we see that we apply some kind of penalty parameter 10 here. So we want to x1 at the moment 1 to be approximately this number. So we also have the analytical solution from book 4 here, and the optimal value phi is represented here. Here we divided our interval in two pieces. That means that p equals 1, and we obtained on the fourth iteration, we obtained such a solution sigma star. It is represented here. We see from the pictures that the terminal condition of x1 is approximately satisfied. So here we have such a number, and it is here, and the obtained value of the functional is also rather close to the true value of the functional. In conclusion, I want to note that I used the apparatus of quasi-differentiable functions. It is results of Vladimir Fedorovich Demyanov and Professor Rubinov. And I also used the control parameterization. It is rather well described in book of Chinese mathematicians here. So thank you for your attention. I will be glad to answer your questions.
Thank you, Alexander. Maybe if somebody wants to ask some questions.
Alexander, I would like to ask you, you have deep theory, advanced theory, and do you have correspondent programming support based on MATLAB or on Maple maybe, or other system?
Yes, I want to note that this algorithm is rather easily calculated is rather easily programmed. So I have a small support in Maple even. So besides, I want to note that the most difficult, I suppose, part of the calculations is this. This theorem here, yes, and it is the calculation of quasi-differentials. And the quasi-differentials are usually on practice are just polyhedrons for each class of functions. And on our department, we have rather good program support made by Todor Angelov, Grigory Tomasyan, and so on, and we both use this in our work.
I believe that you can construct specialized toolbox.
Yeah, it's our plan and our dream to make it effective and use it, of course.
Okay, thank you very much.
Thank you.
Thank you. So I suppose, thank you, Alexander, for your presentation, and we can do break for 15 minutes.
Okay. Алина, можем начинать?
Да, можем начинать.
Okay, ladies and gentlemen, I propose to continue our conversation. So now we have a session, second session of informatics and control processes, part 2. And the next report will be done by Yaroslav Knyazkin. Yaroslav, please.
Good afternoon, ladies and gentlemen. The object of my research is spectral design of optimal fault detection observer based on model synthesis procedure. Let's demonstrate the description of a controlled plant and scale out disturbance. We suppose that it is superposition of a few harmonics with the given frequencies and phases and a step function with known amplitude. Omega sub 0 is given central frequency of the harmonical part of the disturbance. We suppose that the plant can be affected by the slowly varying fault action, F. The structure of a fault detection observer filter is presented on the screen. R is the residual signal, decreasing of which demonstrates that the fault occurs. L of S is transfer matrix to be designed. Let's denote new variables and consider the error dynamics. Then introduce the transfer matrices from the external disturbance and from the fault to the residual signal. Effectiveness of the C-wave filtration is expressed by the following fraction. J, which is to be maximized. The second crucial condition is integral action relatively to the constant external disturbance, such as sea current or wind. The functional J is to be maximized by the choice of a transfer matrix L, guaranteeing stability of the designed closed loop system. Describing the error dynamics. To implement the spectral technique, we consider the auxiliary LTI point received by transposition of the error dynamic. The scalar D sub 1 is a harmonic with the central frequency omega sub 0. Let's introduce the auxiliary functional, mean square functional, and note that it is very close to the function J sub 2 and introduce the auxiliary problem of minimization of the auxiliary mean square functional by the choice of stabilizing controller omega. Sorry, W. When we use the parameterization technique, let's parameterize the set of transfer matrices from the external disturbance, auxiliary external disturbance signal to state vector and control signal of the auxiliary plant. We introduce the parameter phi, where matrices alpha and beta can be chosen in the way presented on the screen, with solving of the following Riccati equation. Let's express the transfer matrices as functions of a parameter phi and rewrite the functional in frequency domain. It can be represented in the demonstrated form, and one can see that the last summand T sub 3 is not function of the functional phi, and as a result we can receive condition of the optimality. The second step is to receive the condition of the integral action in terms of the parameter phi. These conditions can be derived from the presented equations, and the dynamic of the transfer matrix phi on the zero frequency can be derived from the following system of linear equations, where the vector f sub 0 can be parameterized. We know the desired dynamics of the transfer matrix phi on the zero frequency and the frequency omega sub 0, and its elements can be calculated by the presented formula. The polynomial delta sub phi with the desired degree of stability can be parameterized in the presented way. Note that the parameter phi can be considered as function of the parameters gamma and mentioned parameters gamma sub 1. when we receive the parameter transfer matrix phi, we substitute it in the previous equations and receive optimal dynamics of the closed loop system. The controller.
Yaroslav, excuse me, you have only 1 minute.
Yes, can be calculated as solution of a following polynomial equation presented on the screen. Finally, we can maximize the functional by any numerical method. The algorithm is presented on the screen. Finally, we'll demonstrate the practical implementation of a proposed algorithm on the plant with the presented parameters. After optimization procedure, we received the demonstrated transfer matrix and let's present the implementation of the designed observer filter. Here we can see that it does not react to the external disturbance. It is blue line and successfully detects the fault occurred at 250 seconds and does not react on the increasing effect of the constant disturbance occurred at 50 seconds. We can see when the state formulated problem have been successfully solved. Thank you for your attention.
Thank you.
Thank you very much, Yaroslav. You can ask him any question, please.
Maybe I have a small question. Can you back to numerical example slide with numbers?
Yes.
Yeah. How you choose these parameters? You just get n at all, or this is real data or something?
Yes, Alina, it is real data of the longitudinal motion of the marine ship.
Okay. Thank you.
Some more questions, colleague?
No questions.
No question, Yaroslav. Thank you very much.
Can I just check one moment? Mikoni Stanislav, are you here? Our third presenter.
No, Stanislav Mikoni.
No, Stanislav. Maybe somebody knows him and can call him.
Okay, so the next report will be done by Alina Boyko, adaptive methods for an actuarial optimal control problem with dynamic constraints. Please.
Thank you. So, hello everyone. Can you see my screen? It's okay, yeah? Yes, okay. Yes, I suppose it's okay. So, my name is Alina Boyko, and I'm from St. Petersburg State University's second year PhD student. And today I want to tell you about adaptive method for an actuarial optimal control problem with dynamic constraints. So we will consider the one interesting actuarial problem of the Russian insurance market, which can be considered as an optimal control problem. And the interesting feature of this problem is the dynamic constraints for control parameters. So using an actuarial problem as an example, we will consider the application of the adaptive method for solving linear optimal control problems. This approach is based on reduced the optimal control problems to an interval linear programming problem and find the optimal plan using the adaptive method by Rafael Gabasov. So we use this approach because this numerical method allows us to work with dynamic systems and construct for them optimal control values. Let's consider in detail what problem we have in insurance market, in the Russian insurance market. So how you know the insurance market is growing and developing every day, and there are many different types of insurance and two general types in life and non-life. In non-life, we have motor insurance, and everyone who has a car now what is compulsory motor insurance. In Russian, it's called OSAGO, and in English, it's called CMTPL, or compulsory motor third-party liability. Let's briefly talk about what is it, who don't know. If you have an accident and you have an insurance policy, your loss will not paid not by you and not another driver. It will be paid by the insurance company. And this type of insurance allows shifting of financial responsibility to the insurance company. So what we have? In CMTPL, if you have an accident and you're not guilty, you can go to your own insurance company and get your compensation. But if you're not guilty, why your insurance company should pay for your loss? So that is why we have in Russia direct compensation for losses. So it's how it happened. You go to your insurance company and your insurance company pay you loss. And after that, your company can require compensation from guilty person's insurance company. But this is the most interesting fact. This loss is not compensated in full amount. They get back some fixed value, not equal real amount of loss. So let's consider how it happened, in how the process has happened. So it's called Belgian system. Why Belgian, nobody knows. And it's regulated by the government. And so during one calendar session, one calendar week, every insurance company sends their requirements into some system. And after the end of the week, this electronic system divides these requirements into 30 groups. And after that, in each groups, they sorted in order of loss amount and divides into 2 or 3 groups. It's dependent on the total value of the requirements. After that, in each subgroup, the average value is calculated, and this average values get the companies. So they get not real amount, they get some fixed values. It's not a fair system, and let's consider why. For example, we have 2 companies, company A and company B. Company A sent $600 something maybe, and company B sent 800. So they can get, they get 700. For company A, it's a good result. They get all compensation, and for company B is not a good result because they get loss. And so in real life, the insurance market is controlled by several large companies. And if you're a small company, you can't control this process. So, but you can forecast it. How to forecast? I actually don't want to tell in this presentation because we have no much time. We talk about optimal control model for this problem. So, that means that if your average loss less than the average loss in the market, you get your company A, I'm sorry, and if not, your company B, and so get loss. So if we can forecast this fixed value for 5 weeks in advance, we suppose that we need to find some policy for insurance company to send all requirements and get maximum compensation. And also, why this problem is very interesting, because the loss for small company, it's like a few millions in a week. So if we can solve it, it's a good for company. Let's consider mathematical problem statement. This problem can be considered as optimal control problem, and control parameters is the sum of losses that the insurance company sent during the week. And so we have capital at moments of time t, and we have initial capital and the capital of the end of the period. And C is our forecasting fixed value, and the financial results of each week is the function f, and n is the number of requirements. So because the capital growth consists of financial results and the amount of capital depreciation, we have following differential equations, and also we have following constraints for control parameters. We can send more than we have money. Yeah, and so this is important constraints. It's dynamic constraints for control parameter. So finally, we have system 1, and we should solve it. It is necessary for the insurance company find such policy to maximize the number of claims, and so that is why we have this functional. For solving this problem, we use the adaptive method. It's a numerical method, and for implementation, we divide the interval of time into n parts, and our controls is piecewise constant functions, and using the general solution of Cauchy's formula for differential equation, we can get following interval linear programming problem. So in our previous research, we already considered how to reduce optimal control problem to interval in linear programming problem, so I just swipe it. And for numerical experiments, we use MATLAB environment, and we developed several programs for solving this type of problems, economics problems. And so we take following parameters. We want to see what happened during 5 weeks, and we want to have capital in 5 times more than in initial capital. Yeah, and so we compare our adaptive method algorithm with the classical simplex method algorithm. So what we get, what we have, it's in the slide you can see how it looks like our optimal control for the adaptive method. It's a piecewise constant. And so it's our policy for 5 weeks. This is the change of the objective function in each step of the adaptive method algorithm. So we can see that he grows in each steps. And so in conclusion, using an actuarial problems as an example, we considered the application of the adaptive method for linear optimal control problems with dynamic constraints. We found an optimal policy for sending of requirements using the MATLAB environments, MATLAB software, and compared the resulting solution with the simplex method, and also how we can see it's almost the same. And further research will be aimed to improving this approach for nonlinear system of optimal control. So this is references, and thank you for your attention.
Okay, Alina, thank you very much for your interesting report. And the natural questions, do you have any practical implementation with collaboration with any insurance company?
Yes, I work in insurance company, and I already saved for him almost 98 million in a year.
Oh, very well, thank you.
Thank you.
Dear colleague, any more questions to the reporter?
Yeah. Good afternoon, sir.
Hello.
Can you hear me?
Yes.
Okay, Alina, thanks for your presentation. It's so interesting. I have one question. When you started, you said that your method was applied for the Russian insurance markets.
Yes.
So is it applicable to other countries like in the EU or in the US or in, well, sorry, African insurance markets? Is your method applicable or have you tried to apply it? Thank you.
Actually, it's a good question because only in Russia we have this not good process. In other countries we have free market and they just do what they don't have this system. They can direct compensation for losses. This system it's not it's only in Russia.
Okay, so my advice is we also love that you do a more global method that would capture other countries. Like me, for example, I could call you and tell Alina, please, could you sell me your method or could you give me your method? So I would advise that maybe it would be nice to have it as a global method, not just for the Russian insurance industry.
Okay, okay.
Thank you.
Thank you.
I have a question, if possible.
Okay.
Maybe I didn't understand completely. So you're using continuous time model, yeah? But the system is seems to be discrete, like 1 week.
It's a discrete system, and this is dynamic system. And what
But the system, the time is continuous, so it's not discrete.
No, for this problem, it's discrete time, not continuous time.
The system of differential equation you had, yeah?
Yeah, yeah.
It
So
was only initial system in
Yeah.
time.
and then you discretize it like
Yes,
this.
yes.
Okay.
Yes.
Okay, colleague, no more questions. Alina, thank you very much for your interesting presentation.
Thank you.
Okay, the next reporter is Stanislav Nikoni. Please, you can make your presentation.
Да, я здесь. Я прошу у организатора выполнить мой доклад по-русски, поскольку я вижу англоязычный тут только Энтони. А
Ну, есть проблема, мы транслируемся в YouTube, но мы вам позволим сделать так, как вы просите.
Слайды у меня англоязычные, так что я думаю, он поймет.
Я думаю, I suppose Anthony understands in Russian.
Yeah, sure.
Энтони прекрасно владеет русским языком, поскольку у нас учился.
Да. Ну прекрасно, спасибо.
Точно.
Я начинаю доклад, который посвящен модели участников жизненного цикла социокиберфизической системы. Особенности киберфизических систем. Современная тенденция в науке и технике является объединение управляющих устройств с исполнительными устройствами. Это вот embedded controllers, то есть встроенные контроллеры, и они дают новое качество управлению, поскольку программное обеспечение, software, обеспечивает гибкость управления. Режим управления используется автоматический, автоматизированный и ручной. Вот последние два режима, автоматизированный и ручной, предполагают участие человека-оператора. Мы занимаемся проблемами оценивания киберфизических систем, то есть сложных систем, таких как роботы, беспилотники и так далее. Они характеризуются, во-первых, большим количеством параметров. Во-вторых, эти параметры разнородные. Наряду с параметрами такими, как назначение, ресурсопотребление, существуют параметры, характеризующие управление этими системами. И поэтому возникает проблема группировки однородных параметров. народных показателей, индикаторы это показатели, народных показателей, характеризующих свойства вот этих сложных систем. В результате получается многоуровневая структура оценивания. Но вот на практике существует такой эмпирический подход. Внизу показана книга Семенова, где он использует эмпирический подход к построению многоуровневой системы оценивания сложных систем и экспертные методы. Мною предлагается подход, который основан на интересе участников жизненного цикла. К этим участникам относятся проектировщик, изготовитель системы, оператор, он же пользователь, обслуживающий персонал, владельцы ресурсов и другие системы, к которым могут относиться как системы кооперирующие, так и конфронтационные. Вот здесь показана модель социокиберфизической системы. Ее ядром является киберфизическая система. Стрелками показаны, вот этими двойными стрелками показано влияние участников жизненного цикла на свойства системы. Пунктирные линии показывают потребление свойств системы. Пунктирные вот эти линии отражают интерес экономический участников жизненного цикла. И вот эти вот жирные линии показывают управление киберфизической системой. Итак, начинается с проектировщика, который закладывает свойства киберфизической системы, изготовитель, который их реализует, продавец продает эту систему, пользуясь экономическими интересами, а пользователь или покупатель, значит, покупает, соответственно, обслуживает ее обслуживающий персонал, эксплуатационники, а управляет оператор, в любом случае даже высокоавтоматизированных систем. К пассивному окружению относятся ресурсы, которые потребляет система из внешней среды, ну и сама природа, которая воздействует на эту систему, и система воздействует на природу. К внешним системам относятся кооперирующие системы и конфликтующие с ними. Ну, вот здесь кратко рассматриваются интересы участников жизненного цикла системы. Вот это проектировщик, он закладывает свойства в систему, которая должна обеспечить ее высокий технический уровень для того, чтобы она была конкурентоспособной. Ну, и здесь технический уровень обуславливается как общими свойствами системы, так и свойствами отдельных ее компонентов. А стоимостные показатели выступают как ограничительные. Интересы изготовителя заключаются в том, чтобы соблюдать требования технической документации, патентные соглашения, и его интерес заключается в показателях, которые характеризуют технологию изготовления этой системы. Экономические показатели стремятся минимизировать. Интересы пользователя, покупателя и продавца вот описаны на этом слайде. Я даже, наверное, не буду их особенно перечислять. Понятно, что у них у всех в основном экономический интерес к системе. Интересы оператора, обслуживающего персонала и владельца ресурсов. Но оператор заинтересован прежде всего в эффективности работы системы. А обслуживающий персонал заинтересован в минимизации издержек для ее обслуживания. Ну, владелец ресурсами заинтересован, естественно, в пользе какой-то, которую он извлекает из продажи. Интересы тех, кто отвечает за окружающую среду, является минимизация загрязнения окружающей среды. Ну, вот здесь показаны показатели верхнего уровня, которые, собственно, и отвечают интересам перечисленных участников. Выполнение работы в наибольшей степени интересует оператора, изготовление изготовителя, вопросы купли-продажи интересуют вот этих персон, обслуживание интересует обслуживающий персонал, узлы системы проявляет интерес как проектировщик, так и обслуживающий персонал. И, наконец, внешним окружением заинтересованы пользователи, владельцы ресурсов и те, кто отвечает за окружающую среду. А вот следующий уровень уже характеризует выполнение работ. Ну, прежде всего, назначение этой киберфизической системы, которая у разных киберфизических систем различная. А вот что касается качества функционирования, это достаточно стандартные показатели, а именно устойчивость системы, безопасность, эстетические показатели, удобство, естественно, режим управления, ручной, автоматический или автоматизированный, и отношения с внешней средой. Ну, вот здесь подробнее рассматриваются показатели выполнения работы. К ним относятся показатель назначения, показатели качества функционирования, операционного управления и взаимодействия с внешней средой. Ну, к показателям назначения относятся, например, такие, если для транспортной системы, это, допустим, скорость, там, масса, показатели габаритные и так далее. Показатели качества функционирования, к ним относятся устойчивость, безопасность, эстетичность и удобство, эргономика для оператора и комфорт для пользователя системы. Влияние управления на качество функционирования. Но оно зависит от внутреннего контроля и от действий оператора. Качество функционирования, которое обеспечивает через устойчивость и развитие. Устойчивость и развитие. Собственно, это и есть показатели, которые характеризуют управление. Они противоречивы, и тем не менее, значит, методы, обеспечивающие устойчивость системы, это автоматическое регулирование и адаптация. А развитие предполагает выбор путей развития. Он свойственен самоорганизующимся системам. Ну, вот здесь показаны плохо различимые, значит, первичные показатели грузовика. Я его взял из книжки Семенова. И та структура показателей, которые вот он объединил. Значит, вот первое – это функциональные показатели грузовика, дальше операционно-технические, операционно-экономические, окружающая среда, показатели стоимости. Ну, фактически двухуровневая система показателей здесь представлена на этой таблице. А здесь показана структура показателей, которая отвечает уже той структуре, которая предлагается с участием участников жизненного цикла системы. Она трехуровневая, я тоже не имею времени для того, чтобы ее очень подробно пояснять. Вот остановимся на оценке качества вот этих киберфизических систем и социокиберфизических систем. Вообще эти вопросы рассмотрены вот в нашей монографии, которая здесь помещена ниже. Квалиметрия моделей и полимодельных комплексов. Она доступна в интернете, и можно там почитать на русском языке. Что касается иерархической системы показателей, значит, она фактически характеризует исполнительную подсистему киберфизической системы. А для того, чтобы оценить качество управления, нужно еще привлечь оператора. А как только мы начинаем привлекать оператора, значит, необходимо оценивать его компетентности. Более того, для того, чтобы проверить качество функционирования киберфизической системы, мы должны еще руководствоваться физическим и, значит, психологическим состоянием человека-оператора, от которого зависит эффективность управления системой. Эффективность социокиберфизической системы определяется степенью достижения цели. На самом деле это результативность, а эффективность предполагает еще и затраты ресурсов, которые используются для достижения цели. Ну, в заключение следует сказать, что сложная система вместе с теми, кто обслуживает ее, участвует в ее создании, она классифицируется как социокиберфизическая система. Каждый из участников имеет свой профессиональный интерес к киберфизической системе, и эти интересы учитываются вот на верхних уровнях системы оценивания. Предлагаемая система оценивания, структура, она достаточно универсальна и может быть применима к системам любого типа. И, наконец, предлагается выбор оценивания, выбор способов оценивания качества киберфизической и социокиберфизической системы. Спасибо за внимание.
Спасибо, Станислав Витальевич. Коллеги, какие есть вопросы? Ну, Станислав Витальевич, позвольте я у вас спрошу. Значит,
Да.
вопросы устойчивости, конечно, вы сами понимаете, для нашего факультета это принципиально, да?
Да,
Но
конечно.
когда я поднимал этот вопрос на факультете ВМК, там они киберфизическими системами активно занимались, там Дмитрий Евгеньевич Нумиот, Владимир Александрович Сухомлин и так далее. Когда я у них спросил про устойчивость, они меня перекрестили крестным знамением и сказали, вот мы будем компьютерными вопросами заниматься, а устойчивостью, ну, хотите и занимайтесь. То есть, насколько вы видите там все это перспективно, потому что, конечно, это крайне сложно. Да еще с возможностью потери информации в обратных связях. Как вы на это смотрите? Насколько это пробиваемо, так бы я сказал?
Я придаю очень большое значение этому свойству системы устойчивости, потому что, вы знаете, я даже написал, вот, по-моему, в прошлом году у меня была статья по определению понятия управления, и я отталкивался там от фактически второго закона Ньютона. Значит, когда тело, значит, либо оно находится в покое, либо, значит, движется прямолинейно при отсутствии на него возмущающих сил. И отсюда, собственно, и возникает проблема управления. Первая проблема – это вот эта устойчивость, стабилити. Ну, она обеспечивается, прежде всего, системами авторегулирования, а в условиях воздействия окружающей среды еще под системами адаптации, которым, конечно, сейчас придается большое значение. А если мы коснемся развития системы, там, да, имеет место бифуркация, выбор путей дальнейшего развития. Это мы уже переходим на, значит, более высокий уровень принятия решений. Я здесь не рассматривал технические, тем более математические аспекты проблемы устойчивости, но ей придается в управлении, естественно, так сказать, я бы сказал, определяющее значение.
Ну, понятно. То есть вы оптимистично смотрите на эти вещи.
Да.
То есть можно с ними работать.
Да.
Понятно. Спасибо. Коллеги, есть еще вопросы?
Да.
Пожалуйста.
Печников Андрей Анатольевич. Станислав Витальевич, добрый день. Добрый день всем коллегам. Вопрос такой, вот насчет обслуживания сервиса. Понятно, что как критерий минимизации издержек организации, которая занимается обслуживанием, это понятный критерий. Но это ведь зависит от того, каким образом заключены договора между сервисной службой и пользователем. А если будет договор такой, чем чаще я выезжаю на объект, тем больше мне платят. Ну, когда ломается, плохие микроволновки, чтобы чаще их ремонтировать, как бы.
Но проблема обслуживания, конечно, так сказать, она, вы знаете, в советское время мы сами все обслуживали. Если у тебя есть автомобиль, значит, мы, так сказать, его сами обслуживаем. Сейчас действительно обслуживание отделено от других стадий жизненного цикла. И здесь вступают в дело экономические отношения. Да, я сам таким образом чиню свой автомобиль теперь через такие, значит, внешние системы. И, конечно, нужно их включать в проблему оценивания полностью. Ну вот смотрите, когда мы поставляем тоже вооружение, допустим, в другие страны, там же возникает проблема обслуживания. Вот, обслуживающие центры эти все, и, естественно, это должно включаться в общую систему.
Я так просто.
И учитывать это в оценке
системы. Спасибо.
Спасибо за вопрос.
Спасибо, коллеги. Спасибо, Станислав Витальевич. Переходим к следующему докладу.
Спасибо.
Значит, the next presentation will be done by Alexander Popkov, Optimal Program Control in the class of quadratic splines for linear systems. Please.
Dear colleagues, good afternoon.
Станислав Витальевич, пожалуйста, простите, отключите презентацию.
Да, я сейчас пытаюсь отключить, только не вижу как.
А вверху там прекратить презентацию, остановить презентацию. Ага, спасибо.
Да, спасибо.
Александр, please.
One moment.
Есть.
Dear colleagues, my name is Alexander Popkov. I'm a graduate student of St. Petersburg State University, and the topic of my presentation is optimal program control in the class of quadratic splines for linear systems. Let's start from the problem statement. We consider some process. Its dynamics is described by linear system of differential equations with controls, and the terminal conditions is to transfer our object from some initial state x with lower asterisk to the final state x with upper asterisk for the some predefined time big T. And the important detail that we have here two-side constant bounds for the control, and the objective function is minimize integral of quadratic form of control components, where Q is a positive semi-definite matrix. Let the controls be quadratic splines with given with the uniform steps. That means that we split our time segment on big N time subsegments, and on each subsegment control is a quadratic polynomial of time. So the problem is in finding admissible and optimal values of P0, P1, and P2. So actually, in our department, we usually consider the control in the form of piecewise constant functions. So this research is some branch of this research. So in my point of view, there are some advantages. This form, in this form, we can approximate difficult nonlinear functions, and we can achieve continuity and smoothness. And of course, we have such disadvantages as more difficult to solve than for piecewise constant case. I see 2 points of application of such form of the control. First, when for models in which control functions by their nature should be continuous or smooth. For example, for models when the control is velocity, or for models in which smooth movement is one of the goals of the control problem. For example, in the article of Park and Kuipers, considered smooth control for wheeled mobile robots. These robots is need for transport disabled people, and so achieve smoothness is very important for these problems. So solution scheme is just first point, main point, reduce the original control problem to some well-known mathematical programming problem, and second step is resolve mathematical programming problem by standards methods. So let's start. Let's start from the smoothness conditions. So polynomials are smooth by nature, but we must to achieve smoothness at knots. So to achieve this, we acquired neighbor polynomials at knots, and to achieve smoothness, we acquired derivatives of neighbor polynomials at knots. So these constraints are optional, and depending of our problem, if we want to achieve smoothness, we add this constraint. If we not interested in smoothness or continuity, we just remove these constraints. Second is a strain constraints on the controls. So let's insert polynomials instead of controls in bounds, and we have such constraints, but these constraints depends on time. So and we want to receive some constraints, the algebraic constraints that not depend from the time. So first step, we transform these bounds to the extreme condition bounds. So for quadratic polynomials, we have on each interval, we have only 3 points that suspicious of extremum. It's knots and the extremum of the parabola. For knots, it's a very simple constraint. Just insert it in the initial bounds, and it's linear inequalities. So for extremum of quadratic functional is more difficult to simplify our formulas. Let's reassign some variables. So we and introduce new variables y1 and y2. It's just a value of polynomial of in knots. So now we have three variables p, y1, and y2 instead of previous 3 variables. So there is a lot of samples, but this problem is very simple. So we have some time segment from tau1 to tau2, and the upper and the lower and upper bounds L1 and L2. So now let's focus only on upper bound. Our goal is to find the constraints on P depending on the values of y1 and y2. So to achieve this, at least one condition should be satisfied, or the value of the parabola extreme is less or equal than L2 upper bound, or the argument of the parabola extremum is outside the considered segment. So let's resolve such school task. So let's fix our points y1 and y2 and find the values of p when the parabola extremum is equal to upper bound. So it's a solution of such quadratic equation of P that has two solutions. So we can notice that for fixed y1 and y2, we have two situations when parabola extremum is equal to upper bound. First, when this extremum inside the segment. Second situation outside the segment. We are interested only in the first situation, and this first situation corresponds to the solution of this equation with plus in the middle. So repeating the same for the lower bound, we find two-sided constraints to P and depending on variables y1 and y2. So it's algebraic constraints. We can use it, but it's very non-comfortable to use it because that has roots, and this is non-convex. So we can avoid this. Firstly, let's introduce new variables S and add restrictions for them. So meaning of these S variables is just differences L2 minus Y1, L2 minus Y2, and so on. So we rewrite these nonlinear constraints in new variables, but it's still non-convex. It still has roots. So next step is to split variable P2 on non-negative variables R1, R2, R3, R4. The idea of this splitting that R1 in our nonlinear constraint must be response for the linear part of lower constraint. R2 must be response to the nonlinear part of the lower constraint, and so on. And one more important detail that we should ensure that if P2 positive, then some R1 plus R2 must be 0. And otherwise, if P2 negative, some R3 plus R4 must be 0. So to achieve this, we must introduce binary variable delta and introduce such constraints. So it's bad that we need to use binary variables, but it's much more better than use non-convex constraints. So and finally, we can rewrite nonlinear constraints. Firstly, linear part, and secondly, nonlinear part. This nonlinear part is a quadratic constraints, and the type of this quadratic constraints is a rotated second order Kohn constraints. The main
I'm sorry,
property.
Alexander, you have only 1 minute for your report.
Okay, so main detail is that such constraints is have a convex admissible set. So next, I reduce terminal condition. It's just n linear equations. Objective function reduced to the quadratic form of variables p0, p1, p2, and it can be proven that this quadratic form is positive semi-definite if Q is also positive semi-definite. So we have such a mathematical programming problem. They has continuous variables, binary variables, linear constraints, quadratic convex constraints, and convex quadratic objective. According to the definition, it's a mixed integer quadratically constrained programming problem. It must be resolved by Gurobi, Simplex, Knitro, and other solvers. So it's just example, and the result of this example control functions and the phase portrait. So it's all. Thank you for your attention.
Thank you very much. Your consideration seems to be quite exhaustive for the quadratic splines. Who is your scientific advisor?
Nikolai Vasilievich Smirnov.
Okay, thank you very much. Dear colleague, unfortunately, we have no time for the questions. So I believe that you can ask the reporter by email if you have any interest.
But maybe just one question, no?
Okay, one question. Okay, okay.
I see the mathematically it's clear. So you replace an infinite dimensional space by a finite dimensional. No, parameterize the function. But the main question here is why. So why do you restrict control law? So you say that the advantage of your idea is that you get smooth control. But is this advantage or disadvantage? Because normally piecewise continuous control considered.
So I think I said that is a branch of our research. So in my mind, if we need smooth control by nature, we use such approach. If we don't interested in this, we use a constant piecewise approach.
So it seems more reasonable if you consider piecewise constant or piecewise linear without a restriction on continuity. Yeah.
Yeah.
So what is the advantage? I don't really see. So is it faster? Is it faster or it's?
Okay.
Did you try to estimate convergence? I don't know.
For example, if optimal control view has some difficult nonlinear function, maybe it's most preferred to use quadratic splines for this, then use piecewise constant function, because when we approximate difficult nonlinear function by piecewise constant function, we need a lot of time, a lot of number of subsegments. So in my mind, it may be difficult.
Piecewise constant, but if we're using piecewise linear, then we don't need.
I don't know. Maybe yes. Yeah.
So comparing between piecewise linear and piecewise square, I think piecewise linear is better.
Okay, so I hope that if linear function enough for us, so in my model parameter variable p second will be equal 0, and we achieve linear piecewise linear function.
But in this case, we are not able to satisfy the smoothness property.
It is additional constraint.
Alexey, excuse me, you can continue. Excuse me, colleague. Alexey, you can continue in private conversation.
Okay.
We have no time. Excuse me.
Okay.
Okay, Alexander, thank you very much for your presentation. And dear colleague, we have the last report, which is prepared by Andrei Pechnikov and Anthony Ngohiri. So, Anthony, you can make this presentation.
Yes, sir. Can you hear me?
Yeah. Okay.
Okay. Good afternoon, colleagues, and good afternoon to the chair, Professor Vereme and Ms. Alina Boyko. Okay, this is a joint presentation between Dr. Andrei Pechnikov from Institute of Applied Mathematical Research, Karelia, and me, Anthony Wohi from University of Lagos, Nigeria. Briefly about speech outline, we'll be briefly talking about similarity, then normalized compression distance. We demonstrate a little example, then we show the procedure for determining our similarity. Then we look at simple experiments. After that, we look at some questions that need to be answered before we can automate our method. Okay, similarity. All data are created equal, but some are more alike than the others. So we propose a method expressing the similarity. This method is based on a similarity metric that uses compression. It's parameter free because it does not depend on features or background knowledge of the data being compared. Now, on our research, we concentrated more on websites. On the global or on the general scale, the similarity study is all about objects of the same nature, but we concentrate on websites. Now, we have so many websites in the world, and there are so many websites that resemble each other. Now, and in the classification problems in mathematics, there are so many specific features that can be used in classifying websites. But our own main goal is to find one generalized characteristic that will be used in defining whether two or more websites are similar or not. So we go into the main basis of our research, the normalized compression distance as proposed by Vitani and Celebrezzi in 2005. They proposed this method, and this method is based on the Kolmogorov complexity theory. This formula is used to measure how close two or more objects are, how similar they are. So in our own specific example, we are looking at how close two websites are, and then more than two websites. In this formula, Kx denotes the complexity of a specific method of describing a word X, while Ky, that's also similarly the complexity of a specific method of describing the word Y. This specific method might not necessarily be the shortest or the longest method, but it's a particular method. Now, Kxy symbolizes concatenation. Xy means concatenation. You merge two words together, X and Y. So the K, X, and Y, that's the complexity of describing this concatenated word. Now we quickly look at simple example. This string could be our X, this could be our Y, this also could be our Y or our X. Now the length is just an example. To understand our formula, this word has 32 characters, this 32, this 17 characters. Now this word can be described in so many methods, in so many ways, but we chose just one method. And to describe this in our own chosen method, this can be described as write AB, 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 AB 16 times. This is a more complex word, so there is no easier way to describe it other than to write the whole word out. And this is also similar to this first one. Write AB 8 times and C, that's the C. This is just a demonstration. So the description length, that's description. The length of this, that's 17 characters. The length of this, that's 38 characters. The length of this, that's 20 characters. So in our example, we are using the length of description method as our complexity. So it means that the first string, the first word, has a complexity of 17, the second 38, the third 20. From this very simple example, we see that the first string is less complex than the others because it has a lower number of characters in its description, while the second string is more complex than the first and the third. Now we now concatenate these strings. We join the first and the second. Here we join the first and the third. Here we join the second and the third. This is the length. That's the description method, length of description method. I just highlight only one. Here you have to write this 16 times and then you write this. That's this. I note again that there are so many description methods. This is just one we chose. So this is the description length for each. And of course, the complexity of 1 and 2 will be 52, 1 and 3 joined will be 21, and the 2 and 3 will be 51. So using our formula, which we already seen, we compute and get these figures. This is the first word, this is the second word, this is the third word. From our computations, we see that 1 and 3 are very close to each other, because the lower the number, the more similar they are. Now, yes, 1 and 3 is very close, but if you look at, let me go back to the slide. 1 minute. We computed that the 1 and 3 are very close. Visually, you will see that yes, they are very close, because AB are everywhere. Okay, now we go into our own sites. We take 2 sites. We download some pages from each site, put the contents in a text file, and then we compress it using a RA archiver. We'll come to why we're using a RA archiver. And then the size of the archive, we take it as the complexity of describing that website, the size of this archive file. Once we are able to get the complexity of the archive file, we join each page together. When we join them together, we also, by our formula, we calculate the complexity of the concatenated words. And then by this formula, we calculate the distances between the pages of the website. And of course, when we calculate this, we get something like this. We just use 3 websites to test our method. We got 3 websites. We calculated the distance between this, and this, between this and that. And we can see clearly that the last 2, this and this, are closer. Yes, there might be different interpretations why they are closer, but at a closer look, you will visually looking at it, you see that maybe the design on this side and the design on this side, they resemble more than with this. So that could be one explanation why the 2 are very close to each other. Now, on the advice of my supervisor, Professor Pechnikov, he advised that we should also test it on Nigerian websites, which we did. So we randomly chose 10 websites. 5 of them are government agencies in Nigeria, then 3 federal universities in Nigeria. This is an online newspaper. And the last one is a hotel. We wanted to check whether our method will be able to classify these websites correctly. So these are 10 websites. We only downloaded their home pages, put them in text files, I've already explained, archived them, got the size of the archive files, calculated the complexity of each description. Now we calculated the distances, the normalized control distances, and then with this formula, which we've already seen, and we got something like this. This is a distance matrix. It's a symmetric matrix showing the distances between 2 different websites. In this example, websites are represented just by their home pages. Now, once you have a distance matrix, of course, you are talking about cluster analysis. So we ran this through dendrograms to see visually how they are clustered. We had 2 different methods. This first one, single linkage clustering method, and the second one, word method. Okay, the first one, there are so many things to note there, but one of them is 8 and 10. 8, if we check back, 8 is a university website, while 10 is a hotel. So, but they are clustered together, showing that they resemble or they are similar to each other. In our second method, the same, 8 and 10 clustered together, university website being clustered together with a hotel website. So what could be the reason? Well, these are all the analyses of dendrograms showing us that 1, 2, 3, these are government agencies, they were clustered together in the first method, and in the second method, the same 1, 2, 3, they were clustered together. These ones are very obvious since they are from the same government, so the developer could be the same person. Therefore, that could be the interpretation of why they were clustered together. But we look at my first comment on why a university website is being clustered together with a hotel. These are homepages that were compared. There are so many questions and answers, but a quick look at it will tell you that maybe because of the format of the background, bluish color, could have made the dendrograms to see them as similar. But this is just layman's interpretations. There could be other interpretations. So that's why towards the end of our presentation, we have so many questions that need to be addressed before we can really automate these methods. So the first question is, which page should I download? In our example, we just downloaded only the home pages. And of course, a website is not made up of one page. A website is made up of so many pages. So which page, or more precisely, which information are we gonna download from this website? If I'm comparing whether two websites are similar, which pages do I focus on? That's the first question that we don't yet have an answer to. Second question is, how do I interpret? Yes, we are saying that we are collecting the contents of a page. What if the contents are made up of images, videos, and the non-text files? So how do we interpret such as binary word? The third is how many pages should be downloaded, which is partly part of the first question. How many pages should be downloaded? A website can have 100 pages, another website can have 50. So if we are comparing two of them, which number of pages do we choose? Do we choose the 50 or do we reduce, or how? And finally, the fourth question is, which I believe most of us might be wondering, the archiver. Which archiver do we choose best? Yes, we chose RA. RA is just one of the so many archivers there online. We chose RA because of its convenience. But actually, the better the archiver, the better the results and the faster our computations. So these are also a fourth question that needs to be addressed. Once these questions are addressed, then we should be able to automate our method. For the conclusion, we brought in a technique for studying the similarity of objects, or in our concrete example, similarity of websites, and the mathematics behind the normalized compression distance is the Kolmogorov complexity theory. Now, this method comes with so many good features. For example, plagiarism, checking whether two or more websites are similar to each other, or were copied or were stolen, and also to check whether there are disruptions in the structure of websites. But nevertheless, to realize all these potentials, the questions I just listed must be addressed for us to be able to automate this approach, not just automating it, but for a larger group of objects. Okay, thank you for listening. I will be glad to take your questions.
Anthony, thank you very much for your interesting presentation. Dear colleague, have you any question to the reporter? Okay. All are tired. Thank you very much. Thank you.
Thank you, sir.
Thank you.
Dear colleague, ladies and gentlemen, thank you very much for your participation, for collaboration. Особое спасибо Алине Бойко. I wish you success in your scientific researches, and I wish you health, strong health. That is very important for our hard times. Thank you very much. Goodbye for everybody.
Thank you.
Bye-bye. Thanks.
Thank you.
Bye-bye.